Here's a quick overview of electrical safety. Obviously, we can't spend a tremendous amount of time on all the aspects of electrical safety, but basically, you have to always be concerned about stray electric potentials, stray voltages, which can send a current through our bodies, and it's the current that's very, very dangerous to us. It can cause discomfort at very low levels, it can cause injury at higher levels, and death in some cases. So we're going to talk about electrical safety, why it's important to make sure that things are properly grounded, but also talk about a type of circuit called the GFCI, which is very important for wet areas. Now, electrical shock, again, as we talked about, is when electricity goes through the body through unintended sources. It can result in burns, because we're depositing a lot of energy, can heat things up to very high temperatures, therefore create burns. It can disrupt the muscle activity of the body, it can disrupt vital organs such as the heart, which is technically a muscle, causing it to malfunction. And again, electrical injuries can happen a number of different ways and can result in a number of different variety of injuries. Really, the degree of damage to the human body depends on how much current is going through there. Really, if you only have a little bit of current through you, you're just going to be very, very unhappy that happens. It's just not a pleasant experience to be shocked. If the current is much higher, this can result in a disruption of the central nervous system. It can result in burns, and both can potentially be fatal in extreme cases. We also have the length of time, which is important with regard to the injury. The longer the electricity is going through you, the more damage it can do, the longer it can disrupt things, and certainly the part of your body that it passes through is important. One thing that you should always be aware of when you're working with electricity is, first of all, have some sort of meter or indicator that can tell you if there's stray voltage. A multimeter is a good thing. There are also different devices that will light up if they detect a stray voltage. Always check whatever you're near. And certainly, if you don't know what you're doing with electricity, have somebody else who has experience, who has knowledge, handle it. You can get injured, or if you're doing something that is not safe, it can cause a fire, it can cause an injury. In terms of what variety of currents will do, again, it's so varied. It really depends on where the electricity goes through your body. We talked about lightning strikes and how 80% of the people who are struck by lightning actually survive. It's very much a function of which part of the body it's going through. You never want to work with electricity with both hands. I mean, you want it to be off, first of all. Try to always use one hand. And the reason why you do that is if you make contact with one hand and make ground with the other hand, electricity is going to go through one arm, pass right through your heart, and go out the other arm. So your two arms are actually very, very important never to be in contact with something to create a complete circuit. Generally, anything less than 5 milliamps, okay, that's 5/1000ths of an amp, you can't feel if it's less than that. Typically less than that, it's really, really hard to perceive that. Actually, I guess it's less than 1 milliamp. 5 milliamps or less, you'll get shot, generally no damage. Again, you'll just have sort of an unpleasant day. At 10 milliamps, hand muscles will contract. It might be difficult to let go, and this can create a prolonged exposure, which can be very dangerous. At 100 milliamps, if that passes through the body for just a few seconds, this can be fatal. So a tenth of an amp can be very, very dangerous. And again, here we see different amounts here. In milliamps, 0.5 to 1.5 milliamps, you can just start perceiving this. Muscle contractions, 1 to 5 milliamps. Pain, 3 to 10 milliamps. Can't let go anymore, between 10 and 40 milliamps. Um, you can have breathing paralysis at 30 to 75 milliamps, and yeah, around 75 to 100 milliamps, you can disrupt the function of the heart. And although we use electroshocks to actually restart the heart, we can actually stop the heart just as well, creating ventricular fibrillation, which, as we discussed earlier, can be fatal. At 250 to 300 milliamps, the heart stops being able to pump blood, and burns can happen at even greater currents of 5 to 6 amps. So again, very, very important not to come in contact with stray voltage, which is going to force the electricity through your body. We use ground in different appliances because if you have a defective appliance where the hot wire comes in contact with the casing or some other part, if you make contact with that, what is going to happen here is the current, instead of powering whatever device you're holding, is going to go through you and then go to the ground. This is dangerous. Obviously, if the casing is grounded, what happens is the electricity goes through the path of least resistance. You have some resistance. So if this grounded wire is already connected to the ground where the electricity wants to go, a short in this motor will contact with the ground, send the electricity safely to ground, and typically this will trip your circuit breaker. Ground fault circuit interrupters are even better. The way the GFCI works is it can react in a 40th of a second, okay? If it senses a difference in current going out compared to coming back of 10 milliamps, it shuts down. Now remember, 10 milliamps is really, starting to get to that dangerous level where you have difficulty letting go. The reason why this is so important in wet locations is, if you're in a wet location, you have better electrical contact with the ground, which is not good for you. In wet locations, water can carry the electricity to you and carry it away from you. So by law, by code, anything in a wet location, be it outdoors, be it a kitchen, be it a bathroom, all the outlets must be GFI. Okay? And in fact, even, you've probably seen these outlets before. You've got this little red button where you can test it. The black button's test, red's reset. Even if you see outlets that are near these GFCIs and they don't have these buttons, they're still hooked into the GFCI outlets many times. You can actually test that by pushing them and see if they go off. And again, very, very helpful, because if they detect a stray current going somewhere where it's not, they shut down immediately. They're a little bit of a pain in the butt because they're always going off even when they're not supposed to. But again, very, very helpful for electrical safety. The GFCI current, again, works this way. Let's say that the current is going to this particular outlet. We have the current going out through the hot wire, the black, and then we have it returning by this white right here. If the GFCI is within the outlet itself, it will make sure, again, as much current comes in as goes back. If it is actually a GFCI circuit breaker, which you can put in your breaker box, this will cover anything that it's connected to. Again, it measures how much current goes out, how much current goes back. And it does this, we'll see this later on, it does this through Faraday's law of induction. You basically put these two wires, which have equal and opposite currents through them, and there's a pickup coil. Now, as long as you have equal and opposite currents through them, there's no voltage. As soon as one has more current going through it than the other one, by Faraday's law of induction, it's going to produce a magnetic field, it's going to induce a current, and a voltage that'll shut the whole thing down.